love them. They can do all kinds of things, and as technology improves, they get smaller and more powerful. But is there a limit to how small we can get? You see, classical computer processors are made of billions of transistors, which act as on-off switches for the electrons running through the wires inside. When the switch is down, it's as if a wall comes down and prevents the electrons from going through. A typical modern transistor is 14 nanometers long. At this level, classical physics breaks down, and we enter quantum physics. In quantum physics, everything is based on probability. A particle, like an electron, has a certain probability of being anywhere in the world, as described by its wave function. With a transistor, the electron has a minuscule but not zero chance of being on the other side of the wall when you look at it. The transistor that should be controlling computer operations suddenly stops being reliable. Enter quantum computers. Compared to classical bits, which take on the value of 0 or 1, quantum bits, or qubits, exist in something called superposition. At any given moment, the qubit has a certain probability of being 0 and of being 1. We have no idea what state it's in until we look at it, in which case it must decide which one it is. If you think back to a few seconds ago, the electron in front of the transistor was also in a superposition. It was simultaneously in every spot along its wire until you looked at it, in which case its superposition collapsed and it decided where it was going to be. Quantum computers also take advantage of another quantum property, entanglement. Entanglement occurs when there's a connection between particles that's so strong that one reacts to a change in state of the other instantaneously, even from opposite ends of the universe. Spooky, right? Albert Einstein thought so too. He called the phenomenon spooky action at a distance. Think of it like this. Say you and I want to play chess, and we decide who plays what color by drawing lots. If I take these two pieces behind my back and mix them up, when I bring my hands out, neither of us knows which piece is in which hand. Only when I open one hand and find a black piece will we know that when I open my other hand, it'll be a white piece. Same with entangled qubits. If you measure one qubit to be a 1, then you know that when you measure the other one, it'll be a 0, or vice versa. By combining superposition and entanglement, quantum computers can perform all the calculations for complex problems at the same time, making them exponentially more efficient. But that power comes with caveats. Qubits are sensitive to their environments, and they can't stay quantum for very long. The coherence time of a qubit is the amount of time it can maintain its superposition, and the more environmental noise there is around a qubit, the less stable its state is. If a qubit's state collapses prematurely, that could lead to errors in the final result. It's like trying to play a song with random sounds and blaring in your ear. Yes, it's why quantum computers have to be so cold, as little as 10 millikelvin. At these temperatures, particles barely move, giving qubits enough room to stay quantum. So it seems we have an answer to our original question. When we thought we reached our limit with classical computing, we decided to embrace the nature of our quantum problems and invent an entirely new type of computer. And who knows, maybe one day we'll figure out a way to go even further beyond our boundaries. Only time will tell.